Hello again and welcome to our next presentation, which is about the introduction of a basic model of an electric vehicle. Within this presentation, we're going to introduce the fundamental mathematical model of an electric vehicle for the needs of smart charging. So we're not going to talk about all of the elements that describe an electric vehicle, but rather we're going to focus on those parameters that are of interest to representing and modeling the smart charging or the charging of an electric vehicle. So first of all, we need the distribution system or the distribution grid. And when I say the distribution grid, I do not mean all of the branches and the nodes in the distribution grid, but rather the point of common coupling between the distribution grid on one side and the electric vehicle on the other side. And here, of course, I refer to the electric vehicle supply equipment, also known as the EVSE, which connects the electric vehicle to the grid. The electric vehicle supply equipment can be AC or DC. Let's, for simplicity in this slide, focus on the AC level 1 or 2 charging. Depending on the charging power, the charging can be single phase or 3-phase. Through a protection unit, the electric vehicle is interfaced with the distribution grid, and this schematic shows the different elements that are inside the electric vehicle. So in this figure on the left side, we can see how a typical EVSE may look like if you have, let's say, a 7 kilowatt electric vehicle charger in your home. And on the right side, we see some of the components inside the electric vehicle. So once the current passes through the EVSE, it goes into the onboard charger of the electric vehicle, where higher harmonics are being filtered out, and AC electricity is coming in the onboard charger. Then there is usually a cascade of 2 power electronic conversion devices. The first of which converts the AC electricity to DC electricity, and then the second which converts the DC electricity again to DC electricity, but with a different voltage level. So this second converter adapts usually the voltage level of the electricity so that it meets the requirements of the battery pack while considering the communication and the signal sent from the battery management system. So what are these additional units here? We see a battery management system. The functions of the battery management systems are multiple. So one of the functions is the battery management system collects the readings about the voltage of individual cells in the battery, the currents of these cells, and the temperature at different points across the battery pack. Then, one of the functions of the battery management system is to perform an estimation of the state of charge, essentially to estimate the level of energy that is accumulated in the battery and the state at which the battery is charged. This information is usually communicated with the onboard charger because it may need to adapt the voltage level with which the battery is being charged. But also, the battery management system is responsible for protecting the battery from unwanted situations such as overvoltage of individual cells. And to avoid overvoltage, it may equalize the voltage across different cells in the battery. But also, if there is significant overvoltage, it may open this protection unit. So it may open the circuit and stop the charging from the onboard charger to the battery pack. Something like this may also happen if there is a significant temperature rise, which may lead to a fire in some battery chemistries. Not all of these parameters are important to us for the model that we're going to use to represent the charging of an electric vehicle. So from the distribution grid, we only need the voltage of the distribution grid, depending on whether we're talking about single phase or 3-phase. This may also change in the value of the grid voltage. For now, let's consider that we are only referring to the phase voltage of a single-phase electric vehicle charger. Then we also talk about the charging current, meaning the phase current of an electric vehicle charger. Then we talk about the onboard charger within that is housed in the electric vehicle. As we're going to see, what we need is the charging efficiency of this element. The charging efficiency is required because there are some conversion losses. We're going to have various losses across this chain of elements. So not all of the AC electricity that is coming inside the electric vehicle supply equipment is going to be used to charge the battery pack of the electric vehicle. There are going to be different elements across the chain when we see various losses. The most significant here is the charging losses. And then another point that is of high interest to us is the energy that is accumulated in the battery pack. So these are the key elements: the charging power, or the voltage and the current, the charging efficiency, most significantly the charging efficiency of the onboard charger, and the energy that is accumulated in the EV battery. Before proceeding, let's take a step back and talk about the dynamics of the battery charging across time. There are different methods to charge the the battery of the electric vehicle, or batteries in any sense. Usually, the most common one is constant current, constant voltage. This is a method that is described within this slide. However, there are also other methods that can be used. One of them is a constant current, constant power. But other methods are tested as well, especially for DC charging, such as pulse charging and other various methods. So the CCCV charging method does the following. Once the charging of the electric vehicle starts, a constant current is drawn for some time, and the voltage of the individual cells of the batteries is monitored. The constant current is drawn until the voltage reaches a desired level, and once this level of the voltage is reached, we want to keep the voltage of the individual battery cells at this constant voltage, and to do this we need to reduce the current with which the battery of the electric vehicle is being charged. So we have two ranges: a range with a constant current and a range with a constant voltage, and this gives the name CCCV, meaning constant current and constant voltage. Why are we seeing this? Because it means that the power that is drawn from the electric vehicle, or that the electric vehicle draws from the electric vehicle supply equipment, may not essentially be constant across time. And this depends on the internal logic, internal charging logic, guided by the battery management system in coordination with the onboard charger of the electric vehicle. This is most significantly seen on this slide. So what we see on this slide are graphs representative of two different vehicles. The first vehicle is a Hyundai Ioniq 5 and the other is a Tesla Model 3. On the x-axis we see the battery state of charge. So this is the state to which the battery has been charged. And on the y-axis we see the charging power. And we see various colors. We see graphs with various colors. The yellow representing 50 kilowatt charger, the blue representing 150 kilowatt charger, and the orange representing 300 plus kilowatts. So these graphs show DC charging essentially. This is the charging profile of the electric vehicles for DC charging. And what we see is that the power that is drawn from the DC electric vehicle supply equipment is reduced after the state of charge reaches a certain level. And this is not so visible for when we use a 50 kilowatt charger, but becomes significantly clear as we move up the power levels. So when we use charging equipment with higher and higher power. So this blue line shows that the electric vehicle charges with a constant power until it reaches this 80% threshold, after which it reduces the power significantly. And this is why it's usually quite faster to charge the electric vehicle until the 80% state of charge limit. After this, the charging power is reduced, and the power that is drawn from the distribution grid is reduced. We're not going to take into account these nonlinearities in our model, but through this slide I want to show you that they exist, that when we move to charging with higher powers, that these nonlinearities exist. There is a clear dependency of the charging power from the battery state of charge, meaning that the charging power reduces as the state of charge is reduced. Why are we going to neglect these nonlinearities? Well, if we use chargers that have a 2.5 or 2.4, 7 kilowatt, or even 11 and 22 kilowatt power, then we can assume that for most of the state of charge range, the battery is going to consume a constant power. These nonlinearities, as I shared, occur for higher and higher powers. But it is worth knowing that the battery state of charge can impact the charging power of the electric vehicle at higher charging rates. Now, let's talk a little bit about the charging efficiency. There are multiple elements where energy losses occur. Firstly, we have the cables with which the electric vehicle is connected to the electric vehicle supply equipment, and also the cables from the electric vehicle supply equipment to the rest of the distribution grid. Then we have the power electronic converters, the AC to DC and the DC to DC conversion. Furthermore, we have battery charging, the losses that occur within the battery charging, one of which is the coulombic efficiency, and the other is the losses that occur due to the heat. So the coulombic efficiency refers to the inefficiency that indicates that not all of the charge that goes into the electric battery increases its state of charge. This is one form of a loss, but the other form of a loss is the heat loss. Actually, so even if the energy accumulated in the battery increases, it is going to have some standby losses because the temperature of the battery also increases, so it dissipates heat to the outside. There are also losses or power drawn from the cooling systems of the battery, and other losses that reduce the energy that is accumulated in the battery that can be modeled as some standby losses of the battery. So what are the ranges that we're actually expecting? Well, depending on the length of the cable and the type of the cable that is used, we can expect 1 to 3% loss in the charging cable. The power converter devices, the efficiency can range between 70 to 97%, and I'm going to talk a little bit about this in the following slides. Then we have the coulombic efficiency, which is usually 1 to 2%, but essentially can be assumed to be 1%. And the battery energy losses, which is the fraction of the energy that goes inside the battery and comes out of the battery, which is around 95%. Then again, we can add the additional standby losses, such as the losses from the cooling system and other losses from peripheral electronic devices that consume energy from this battery, which is let's say 1 to 2%. So quite low losses. So the major losses that we need to take into account here are the power electronic converter losses. This leads me to the efficiency of the onboard charger. Let's represent the efficiency of the onboard charger with this eta as the fraction between the DC power and the AC power. This efficiency is going to range mathematically between 0 and 1, but essentially is going to be larger than 60 or 70%, or 0.6, 0.7. As we discussed before, what we want to now show is that the charging efficiency is essentially not constant. It depends on the loading of the power electronic conversion devices. So this graph here conceptually shows that as the loading of the onboard charger increases, so does the charging efficiency. We have very low charging efficiency for very low loading of the charger, and the efficiency increases. This characteristic is going to differ from one charger to another. Its peak may be around 80%, or it may be around 90 to 100%, depending on the topology and the type of the charger. So why is this important? Well, when we talk about smart charging, we want to be able to modulate the power with which the electric vehicle is being charged. This means that we essentially will lower the current that the electric vehicle draws from the distribution system. How low can we go with lowering the current? Well, according to this IEC 61851 standard, the minimum current that the electric vehicle supply equipment can draw from the distribution system is 6 amperes. So we cannot go lower than 6 amperes. But let's consider a case when we have a single phase 2.7 kilowatt charger. If we charge the electric vehicle with a current within this range from 6 to 12 amperes, we can see that the charging efficiency is going to range between 80 to, let's say, a 95% or 99% if we have a very, very efficient power conversion device. However, what happens if we have a single phase 7.4 kilowatt electric vehicle charger? Well, in this graph, we see that the minimum current that can be drawn, this 6 ampere current, is somewhere around here. And if we map it in this characteristic, we can see that the efficiency is around 60%. So this is a significantly lower efficiency. So let's say if we charge the electric vehicle with a range from 6 amperes to something around 15 amperes as before, which was 12, so between 6 and 12 amperes, the charging efficiency is going to be between 65 and 80%, which is significantly lower than this efficiency here. And then if we go up with the charging current towards the nominal value of this onboard charger, we can also see that the charging efficiency increases. One may say that the nominal value, if the nominal value of the current is pursued, and if the electric vehicle charges with the nominal current, we should not expect significant losses. And this is true, of course. But if we reduce the charging current in order to meet some outside need, let's say in order to avoid overloading the distribution system, we need to be considerate of these additional losses that we introduce through the process. So the main takeaway here is that modulating the current with which the electric vehicle charges increases the energy losses. So with all of this in mind, let's move to the simple model of the electric vehicle. We take into account the power, the voltage, the current, the efficiency, and the energy that is stored in the battery. Of course, we have the power calculated as voltage multiplied by current, and we introduce this equation to represent the energy that is accumulated in the battery at a point in time t. This is equal to the energy that was accumulated in the battery at an earlier point in time when the charging started, which is t0, plus the charging efficiency times the integral of p dt from the point t0 when the charging starts until point t when the charging ends, or this t may also indicate the charging the point in time right now. Please be aware that this symbol eta, which symbolizes the charging efficiency, has now been taken in front of the integral as a constant. Why have we done this when we have discussed in so much length that the charging efficiency can vary? Well, we can of course say that the charging efficiency is a function of the power, and if this is the case, we can describe it with a, let's say, quadratic equation or some logarithmic or exponential equation as a function of the power and include it back in the integral. At this point, for simplicity, we assume that the charging efficiency is constant and we take it in front of the integral. So again, I of t denotes the charging current of the EVSE at time t. U of t is the measured voltage at the point of common coupling between the EVSE and the distribution grid at time t. P is the charging power of the EVSE, so how much power the electric vehicle supply equipment draws from the distribution grid at time t. E of t is the energy that is accumulated in the battery at this point in time, and this is the charging efficiency, which is assumed to be constant. This is a continuous time domain model of the electric vehicle, or the charging of the electric vehicle, and essentially this equation is representative of any storage device. So it can be it can also be used to describe an electric battery outside an electric vehicle, or some other form of storage, for instance a thermal storage, let's say. But at this point, for this electric vehicle, we use it to describe the charging of the electric vehicle, or the battery in the electric vehicle. As this is a continuous time domain model, we want to make it a bit more practical for computation, so we introduce a discrete time domain version of this model. We do this by introducing time slots delta t, which are of course of some finite duration in time, which can be 1 or 2 seconds, or even 5 minutes, 15 minutes, or even 1 hour, depending on how granular we want our model to be. The lower this delta t or this delta tau, the higher the resolution and the accuracy of our model. But essentially this is the same equation, which says that the energy that is stored at a time t is equal to the energy that was stored at time t0 plus the energy that is added between t0 and t. The power is measured in watts or kilowatts. We multiply it by hours, so we get kilowatt hours, and multiply it by the charging efficiency in order to take into account all of the losses in the conversion from AC to DC. So from power taken from the distribution grid and to the power that comes into the battery itself. We're going to use this model to represent some basic use cases. And these are the basic use cases that we are going to introduce. So when we talk about smart charging, we cannot go further down without talking about load balancing, improving solar PV self-consumption, providing ancillary services, and power sharing and scheduling. Most of these use cases or these functionalities are already built in various electric vehicle supply equipment. So if you buy an EV charger that you can install in your home, you may find many chargers that provide lots functionalities such as these. So load balancing, improving solar PV self-consumption, providing ancillary services, power sharing and scheduling. In the following videos, we're going to talk about what each of these means and how we can represent them.